We're going to talk about a thing on a spring and how to analyze its energy when it's in its different positions. And we're going to deduce something about the speed about which this thing is able to do what it's doing. So the first thing we need to talk about is like what's going to happen if you put a thing on a spring and then let it go. So right now in this position, I have a 15 Newton per meter spring, and I've attached 900 grams to it. That thing right now is sitting at the spring equilibrium. So the spring is just loose. It's not floppy, but it's also not stretched at all. So that's the highest this thing can go. If I let it go, it's going to fall all the way down to the place where the spring stops it from moving. So you can see the spring getting longer and longer and longer, stretching more and more and more, pulling back harder and harder and harder, until it reaches its maximum extension. Okay. And then there's going to be a place somewhere in the center. And that place in the center is where the spring pulling up and the force of gravity pulling down balance each other perfectly. So if you've ever watched something go back and forth on a spring, if you let it go, it falls past that point to this point, the maximum extension. But when you're down here, the spring pulls it back up, which means that that spring's force is greater than gravity, so it's able to pull it back up. But there is a place in between there where if I took my hand and I settled the spring at that spot, that it would just hang. That place is we're going to label that as the load equilibrium. Load is just referring to this 900 kilograms. And that's the place where the force of gravity equals the force from the spring. Now, I've got the mass and I've got the K value, so I can actually calculate this and find this location pretty easy. So I'm just going to park those numbers in. Force of gravity is mg. Spring forces are kx, x being the amount that we've stretched. So the mass is 900 grams, 0.9 kilograms, 9.8 for g. K is 15 newtons per meter, and x is unknown. 0.9 times 9.8 gives me 8.82. So if I divide both sides by 15 to move this, then 8.82 divided by 15 gives me 0.588 meters. I apologize for using grams up there, but the idea of suspending 900 kilograms from a spring just makes me too nervous. That's a pretty big object. So in order to keep the numbers manageable, I had to use grams there. So just keep that in mind when you're doing your problems that you have to convert to kilograms. All right, lovely. So I have 3 different positions that this thing is in. So I'm going to have to do a little bit of work to find out something about gravitational potential because it's up, elastic potential because it is stretched at some point, and kinetic energy because it is moving back and forth between those 2 spots. So I'm going to set myself up a chart at my 3 places, spring equilibrium, load equilibrium, and maximum extension, where I'm going to calculate the gravitational potential, the spring potential, and the kinetic energy. All right, so first thing, at the spring equilibrium, this thing isn't moving. It comes to a stop and then it falls back down. So when it does that, it has a speed of 0. So at that place, speed is nothing. Therefore, the kinetic energy is 0. The same thing is going to happen at the maximum extension. If I let this thing fall, it will come to a stop before the spring turns it around and throws it back up in the air. So down here, at the maximum extension, speed is also 0. Therefore, kinetic energy is also 0. All right, now for here, I have MGH, so I need to know what the height is. But I don't have that labeled anywhere on here. I do know that at this place, at the spring equilibrium, the spring is unstretched. So when I fill that into 1/2 kx squared, I can see that this will end up being nothing. If I go down to this place, I know that my maximum extension means that I'm at the very bottom of this problem. So I'm going to decide that spot is h equals 0. And if h equals 0, then gravitational potential will be 0 as well. All right. Now you see between these two things here, if that's 0, and that's the maximum height, and this is unstretched, and this is maximum height, do you see how the height of this thing is equal to the amount of stretch there? So whether I'm saying it's this far up from its maximum extension or the spring extends this far down from its maximum height, it doesn't matter. It's passing through the same distance. So at maximum extension, right, the stretch at max is equal to the height at max. So whatever that is. So the way I'm going to figure that out is I'm going to look at these energies, right? It's not moving up here, so there's no kinetic energy. The spring is unstretched up here, so there's nothing stored in the spring. It's all gravitational potential. At this position, it's not moving, and there's no height, so it's all elastic, which means that any energy that was in this term has to have poured entirely into the elastic energy down here. So I'm going to calculate that in this little space here. Switch colors so it doesn't blend into the other one. I want to know what happens if I equate these two. So the gravitational potential at the maximum would be mgh. And the elastic potential at the maximum stretch would be 1/2 kx squared. And I don't have enough information here. I've got an h and an x. But all that jibber jabber there, saying that this number, right, the height at maximum and the stretch at maximum are the same value, it's going to let me replace this with an x or this with an h. I'm going to decide to replace it with an x just because I can. So the mass, I've got 0.9, g is 9.8, this thing is an x, I've got 1/2, k is 15, x squared. All right, 0.9 times 9.8 is 8.82. Half of 15 is 7.5. Now I have an x on both sides, which means I can divide them out unless x is 0. So I'm going to do that. That leaves me with 8.82 equals 7.5x. And then to finish, 8.82 divided by 7.5. 82 divided by 7.5 gives me 1.176. Or that case where x was 0, because if I can make that 0 and that 0, it zeroes everything out. Now, if you look at those numbers, up here, x was 0. So if x is 0, then the height must be this thing, 1.176 meters. Down here, if the x has to be 1.176, then the height has to be 0. So I can use this as the maximum height because it will rise 1.176 from the very bottom of its stretch. Or I can use this as the stretch if it's at that particular place. So up here I can calculate a gravitational potential, mgh, which will be 90 grams, 9.8 times 1.176 gives me a grand total of 9.8 10.372 joules. Okay. Now down here, 1/2 K, which is 15, times this stretch squared, 1.176 squared, gives me 1.176 times 1.176 equals times 15 equals divided by 2 equals 10.372. Which is good. That's how we set it up, right? I wanted to know when these things were equal, what it's at that particular stretch. So in this position, there's 10.372 joules of energy available, and it is stored entirely as gravitational potential energy. In this position, the maximum extension, there is still the same amount of energy, 10.372 joules, but it is stored entirely as elastic potential. So what happens here at the load equilibrium? Well, I already worked out that stretch, right? It's 0.588 down here. So this distance would be the max stretch minus this stretch. So if I take 1.176 and I subtract 0.588, I get 0.588. It turns out this thing here is dead center. So you can use that fact to check your work later. So when you get one of these stretches, it should end up being twice whatever this number was that we calculated the load equilibrium for. So at that place, it's 0.588 up from the bottom. So it will have a gravitational potential energy. So 15, sorry, its mass is 0.9, G is 9.8, and this thing is 0.588 up from the lowest point. That gives me a total of 0.9 times 9.8 times 0.588. It's 5.186 joules. Okay, so this is at the equilibrium part. Now, that's not everything, right? I was expecting 10.37, but that's only part of it. At this place, the spring has also been stretched a little bit, that much to be specific. So I will have some spring energy there. It's 1/2, the K value is 15, times the amount of stretch squared, which is 0.588. So if I work that out, 0.588 times 0.588 times 15 divided by 2 gives me 2.593. All right, now if I add those two things together, I'm hoping it's 10.372. 2.59, 2.593 plus 5.186 gives me 7.79. Sorry, 7.79. All right, now that's not 10. So where to go? Like energy can't be unaccounted for. Well, it's this. It's the kinetic energy. At this spot, it's either traveling that way on its way to the maximum extension, or it's returning this way to the spring equilibrium. So when I'm here, it not only has some gravitational energy and some spring energy, but it also has kinetic. And that's how this thing is moving, right? Some of this energy that was stored is still involved in being up and stretching the spring, but not all of it. There's a piece that's missing, and that piece has been converted into kinetic energy to help this move. So how big is that piece? Well, it's the total, 10.372. Subtract whatever it is that I'm not using for stretching and being up. So if I take that 10.372 minus 7.779, 10.32, no, 10.372, subtract 7.779, I get 2.593. So this much energy is being used to allow this mass to travel. So if I go up and I calculate kinetic energy, 1/2 mv squared, and I give this object 2.593 joules worth of energy, half of 0.9 is 0.45. Divide this by this, and square root, I should be able to get my V. 5.95, square root of my answer, I get 1.65 meters per second. And whenever you use a square root to break a square, you end up with plus or minus. So that speed can be positive, right, on its way back up to the spring equilibrium, or it can be negative on its way down to the maximum extension. It doesn't matter which way it's headed, the energy works out. So after all this analysis, when you're up here, all of this energy is stored as gravitational potential. When you're down here, all of the energy is stored in the stretched spring. But in the middle, those energies are rapidly converting back and forth between each form in order to allow some energy to be left over for kinetic energy, for speed. And at this load equilibrium, that's where your maximum speed is going to occur. And if you look at the numbers, do you notice that this and this matched? So at best, in this sort of machine, half of the energy is still gravitational potential at this port. A quarter of the energy is into stretching the spring, and you're allowed to use a quarter of the total in order to drive your maximum speed. All right, so at all three places, all three flavors of energy have been accounted for, and accounting for the kinetic in this one row has allowed us to calculate a maximum speed. The last thing we need to do for a simple harmonic oscillator is to calculate the amount of time it takes for this thing to execute its trip from the very top to the very bottom. And fortunately, it's just a formula. So the time it takes for a thing on a spring to execute a full stretch down and a return to its height is 2 times pi times the square root of the mass divided by the spring constant. So I'm just going to get this off my face here. This 2 pi, that has something to do with a full cycle of sines and cosines, or a full circumference around a circle, right? Like anything that repeats itself over and over again seems to have a 2 pi in it. If I made this thing heavier, right, so I increased m, it would take more time to do it. So I need an m in the numerator, so that bigger mass means bigger time. If I put this on a more powerful spring, so a bigger number down here, a bigger number down here means less time. So a more powerful spring should be able to return it more quickly. So for this particular one, if I pop that in there, 2 pi, my mass is 900 grams, my K is 15. So this 0.9 divided by 15 is 0.06. If I square root that, I get 2.245 times 2 times pi 1.539 seconds. So there you go. We have mastered everything there is to know about this particular system. I know where all of its energies are. I know what its maximum speed is as it passes through the center. I know how far it has to drop before the spring turns the thing back around. And I know exactly how much time it will take for the thing to drop to its maximum extension and return to spring equilibrium. So with a little bit of analysis of the energy, we'd be able to master this. There's nothing about this problem that we have left to solve. So in the practice problem, it's basically the same thing. I want to know how much time it takes, how much distance it's going to take, how much energy is in each position in each flavor, and then how fast will it be traveling as it crosses the midpoint.